You may have seen that in this series of videos, I'm drawing a lot of pictures. I'm going to keep doing that because I think it's incredibly useful, especially when we have physical situations that are changing. A spotlight on the ground shines on a wall 12 meters away, and a man is 2 meters tall, and he walks from the spotlight toward the building at a speed of 1.6 meters per second. We are asked how fast the length of his shadow on the building is decreasing when he's 4 meters from the building. Let's get a drawing of this. All right, here's my very detailed drawing here. We've got a spotlight on the ground shining at a wall and a man that's walking toward the building. We're told that the spotlight is 12 meters away from the wall and that the man is walking away from the spotlight toward the building at a speed of 1.6 meters per second. I'm going to make a bunch of copies of this dude and we'll see what's going on in the dynamic situation. The shadow is made because the man is blocking the light. Duh, right? And when the man is close to the spotlight, the shadow that he's going to cast is going to be kind of high. As he moves away from the spotlight, the shadow that he's going to cast is going to get smaller and smaller until eventually, when he's at the wall, the shadow will be exactly the same height as our friend, right? So we have a shadow that is decreasing in height as the man walks to the wall. We want to know how fast that change is happening when he's 4 meters from the building. For this, I want to look at just one shadow in particular, okay? And what you can see is this creates a right triangle. Well, I mean, kind of. Okay, hang on. For this mathematical model, we got to assume that the spotlight is coming from a point directly on the ground. And so we then have a right triangle. I'm going to redraw this black right triangle. Let me move this over and then we'll see what we actually have. What we actually have is two similar triangles inside the big black triangle. One of them is defined by that little angle at the spotlight and the height of the man. The other is defined by the entire distance between the spotlight and the wall itself. Here are our similar triangles. And we know that the height of the little gray one is going to be 2 meters because that's how tall this guy is. And the length, the bottom length of the blue one is 12 meters. And I think that one's obvious. Now, let's talk about what it is that we're trying to find. I want to know how fast this shadow length is decreasing. And so whatever that length is, I want dl dt essentially. So if I call this the length of his shadow, if I call this L, then when we see how fast is it decreasing, I can see that we want dl dt. That tells me that I need to label something L, and it's going to be the length of the shadow here. I went ahead and worked with set up the similar triangles without saying why it was similar triangles here. But I mean, it's a common strategy that we use in these problems. And the reason I want to use similar triangles is I want to use a proportion. 2 is to L as something is to 12. What's going to be the something? I'm going to call that X. It's an unknown length because we don't know how far the man has been walking. Yeah, okay. When he's 4 meters from the building, that is going to be a distance of 8. But it's not always 8. Our friend is walking, right? Besides, if I made this 8, then I would know what L is. Everything would be fixed and nothing would be changing, right? So I need this distance to be changing. I'm going to label it using a variable. And using similar triangles, I know that X over 12 is equal to 2 over L. Keep in mind what we want. We want dl dt. Having L in the denominator here isn't doing me a whole lot of good. So I'm going to take the reciprocal of both sides here. L over 2 is equal to 12 over X. And then I can say L is equal to 24 over x. And now it's fairly straightforward for me to find dl dt. dl dt is equal to negative 24 over x squared times dx dt. You'll note that I use the power rule, envisioning x in the denominator as being x to the negative 1. That negative comes out front. Subtract 1 from the exponent, it becomes now negative 2. Now remember, we saw that we want dl dt when the man is 4 meters from the building. Another way to put that is we want dl dt when x is equal to 8. Don't forget that we have that he's walking at a speed of 1.6 meters per second. That means dx dt is increasing at 1.6 meters per second. So dx dt is equal to 1.6. We have enough to find dl dt. Substituting 8 in place of x and 1.6 in place of dx dt gives us a negative 0.6. Therefore, the length of the shadow is decreasing at a rate of 0.6 of a meter per second. Now, how do I know it's decreasing? It's not just because the problem said so. This negative here is telling me that the change is in a negative direction, and so this is telling me that it's decreasing.